All right, exam for essay question number 4. Let's go over the question. Explain Dalton's laws and Henry's law, Dalton's law and Henry's law, and how these laws are used to explain PO2 and PCO2. Explain the alveolar gas equation and how the information it gives us might be used. Finally, explain ventilation and perfusion ratios and give examples of what might cause these ratios to change. In part 2 of this essay, explain total pulmonary and alveolar ventilation rates and describe why slow, deep breaths are more beneficial than rapid, shallow breathing. In part 3 of this essay, long one, describe COPD and restrictive lung disease. Between these two diseases, mention what emphysema would be, and then explain the mechanisms of air trapping in emphysema. All right, so let's go over our gas laws. First is Dalton's law, and Dalton's law states that the total pressure exerted by a mix of gases is equal to the sum of the partial pressures of each individual gas. So, give you a little write-up. Each gas in the mix behaves independently, and it adds to the total pressure based on its own partial pressure. So let's say that we have 1 atmosphere of pressure, and in that atmosphere of pressure there's a mix of gases. There's going to be O2, there's going to be nitrogen gas, there's going to be CO2. Let's just work with those 3, okay? In our 1 mix of gas, 1 atmosphere, let's say that this is 0.3 atmospheres. Nitrogen makes up 0.4 atmospheres. And CO2 makes up the remaining 0.3 atmospheres. It'd be embarrassing if I couldn't do math equal to 1. So yeah, each pressure of gas, each pressure that it exerts, adds up to 1. So within the atmosphere that we breathe, which is equal to 1 atmosphere, there are different gases that each add to the total pressure. And so if we know the total pressure, we can essentially figure out these ratios and how much gas is involved in making up that pressure. All right, Henry's law. Henry's law has to do with the solubility of gases in liquids. Let me go to the text here a little bit. It's important to know. So, carbon dioxide, just as an example, will dissolve in blood, which is a liquid. And there are 2 factors that will determine how willing it is to be dissolved into the liquid, into the blood. And the first is the partial pressure of the gas pushing down onto the liquid. And so if the pressure of the gas on the liquid is high, the movement of that gas into the liquid is going to be favored. So the CO2 will move into the blood if there's more CO2 near the blood. Obviously, more pressure, more gas. And part 2, the other factor that affects it is the solubility of the gas in that particular liquid. Carbon dioxide is, from the book, 24 times more soluble in water or plasma compared to oxygen. And then nitrogen is half as soluble as oxygen. So carbon dioxide is easily soluble, oxygen less so, and nitrogen even less. So that's Henry's law. Boom, 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 boom. And in the respiratory system, that'll explain how oxygen and carbon dioxide dissolve into our blood plasma. So the partial pressure of each gas will determine how much of it will dissolve. Going back to Dalton's law, there's going to be a mix of those gases, and that'll exert a pressure. And so if there's a higher partial pressure of oxygen in the alveoli, for instance, then more oxygen will dissolve into the blood as compared to the CO2. All right, moving on. The alveolar gas equation is how we understand the balance of oxygen and carbon dioxide inside of the alveoli. So I wanted to also pull this from the book just so I don't get this wrong. so I can explain it well. Because it is important, and there are bits and pieces that go into it. So, our partial pressure inside of the alveolus is obviously going to be pertaining to our oxygen. And so how we determine that is we have to find first the fractional concentration of how much oxygen we breathed in. So that is going to be expressed as fractional inspiration O2. And we're going to multiply that by our atmospheric pressure, which at sea level is 760 millimeters of mercury, minus the water vapor pressure, which is normally 47 millimeters of mercury at normal body temperature. So P H2O. And then all of that is going to be minus, sorry, ran out of space. I write too big. Oh, whiteboard is horrible. So all of this minus our pressure inside of the arteries of carbon dioxide divided by R, and that is our respiratory exchange ratio, which we have determined is 0.85. So that is our alveolar gas equation. Again, I'm going to go through and put in the values that we kind of just assume. 760 there, 40 there, and then 0.85 here. So really what we have to find out is how much oxygen is inspired or breathed in by us, and that can be higher if you're on like an oxygen supplement, an oxygen tank, versus the pressure of carbon dioxide arterially inside of our blood already. So really it helps us estimate the efficiency of the gas exchange inside of the lungs. And if we know the values of our, if we know this value of our oxygen that we breathe in and our pressure of the CO2 already in our bodies, we can determine how well oxygen is being transferred from the alveoli to the blood. So if there's a lower than expected oxygen that we're breathing in, that might indicate some problems with our alveolar ventilation or diffusion impairment inside of the blood. So that can be quite problematic. Also, these values aren't set. Obviously, the atmosphere of the pressure is going to go down as you get higher in elevation. If there's more water vapor pressure in your blood, if there's more of that, then that's going to be a higher value. And then also the respiratory exchange ratio, if that is being affected, whether by if you're exercising or how fast you're breathing and how deeply you're breathing, that can change as well. All right, going over our ventilation and perfusion ratios, that's how we understand our respiratory efficiency, which also plays into this. Our ventilation refers to the airflow in and out of the alveoli, but perfusion refers to the blood flow through the pulmonary capillaries. So this ratio that we have of ventilation to perfusion is, it really determines our gas exchange efficiency. So ideally what we want is ventilation and perfusion should be matched to maximize our gas exchange, obviously. More O2 for less CO2, or vice versa. However we need it for our bodies. People are different. So conditions such as pulmonary embolism or airway obstruction, that can affect our ventilation to our perfusion ratio. And so pulmonary embolism is going to reduce our perfusion, and airway obstruction is going to decrease our ventilation. and that'll disrupt the ratio. So a higher ratio of perfusion to, ventilation to perfusion, a higher ratio indicates that there's more ventilation than perfusion, while a low one indicates the opposite, more perfusion than ventilation. So these mismatches can lead to just bad gas exchange and hypoxemia over time. Okay, go back to the question, make sure I'm covering everything so far. What might cause these ratios to change? Okay. Gotta find where I left off. All right, so ventilation rates and important of breathing patterns. So pulmonary ventilation is the total volume of air moved in and out of the lungs per minute. And this is calculated as tidal volume times respiratory rate. So our tidal volume times rate. Our alveolar ventilation is the volume of air that reaches the alveoli per minute, and that's more relevant to us for our gas exchange and how effective that is. So deep, slow breaths are going to increase our alveolar ventilation more effectively than rapid, shallow breaths. And that's because deep breaths minimize our dead space ventilation, making sure that more air will reach the alveoli. Yeah, gosh, I can't speak, I'm sorry. And that'll enhance our oxygen uptake and the removal of carbon dioxide. Rapid shallow breathing is going to ventilate the dead space mainly within our bodies, air that is just sitting there and provides no oxygen, no value to us, and that will lead to less efficient gas exchange. So go deeper into this with the dead air. I think it's important to understand. So when we breathe, there's dead airspace, and this is alveolar air that doesn't contribute to our gas exchange just because our lungs are getting in the way and the gas can't pass over into the it can't pass through the respiratory membrane. There's also anatomical dead space, and it doesn't really bother us with our gas exchange, so I'm not going to cover that. And then there's also physiologic dead space, and this is the total of anatomical and alveolar dead space, so adding those two up. And so because of dead space, only part of the air is getting down into our lungs, into our alveoli, to be entered into our body to be part of the gas exchange. So when we breathe in, say we breathe in 500 milliliters of air, and I'm again taking this image from the book. It's a good one. Just draw it for you. If we take in 500 milliliters, 150 of that is calculated to be dead air, and then 350 of that is going to be fresh air. So we're losing 150 milliliters of air. Only 350 is making it into our lungs when we breathe in, versus 150 say that we breathed out or was just not useful to us. Say we breathe in nitrogen or CO2. That's 150 milliliters of air that doesn't really bother us. And so once we breathe that in, it's going to go into our gas exchange. And coming into our gas exchange, there's only going to be 150 of that 350 that is going to be used in the gas exchange. And so when we exhale, it's going to be the full 500 milliliters that we originally breathed in. But 150 of that is, 350 of that is going to be stuff that we just breathed from the gas exchange. 150 of that is going to be the dead air that we originally breathed in. It's useless to us. So really what we're using is 350, and even a portion of that isn't even used in our bodies in the gas exchange. So that's a little bit about dead air or dead space. All right, going back to the question, make sure I got everything. Slow, deep breaths, rapid, shallow, better expansion of the alveoli, allowing that anatomical dead space to be removed from this equation, and more time for the alveoli to catch that oxygen and add it to our bodies. All right, part 3, COPD and restrictive lung disease. Between these two diseases, mention what emphysema would be, and then explain the mechanisms of air trapping in emphysema. Super, super fun. Okay, so COPD stands for chronic obstructive pulmonary disease, and that's characterized by airflow obstruction, and that can really be bronchitis, chronic bronchitis, and emphysema, obviously. I've had bronchitis before. It sucks. It wasn't chronic, though, so that was good. Restrictive lung diseases, on the other hand, are more like reduced lung expansion due to stiff or damaged lung tissue, and you'll see this in smokers, I think. Yes? Yeah. Anyways, emphysema is a type of COPD, and that involves the destruction of our alveolar walls, and so that's going to increase our air spaces, and it's going to reduce the elastic recoil of the lungs. So this causes air trapping, where air remains in the alveoli during exhalation, which obviously reduces the efficiency of our gas exchange and breathing. Air trapping in emphysema results from the collapse of small airways during exhalation, and that'll prevent complete expulsion of all the air in our lungs. And this leads to increased residual volume, decreased gas exchange efficiency, and obviously it's very uncomfortable when you can't breathe in or breathe out fully, and just so. I think that really covers it. COPD, yeah. Bronchitis, airflow obstruction, air trapping, got that. Okay. Restrictive lung disease, when your lungs just aren't elastic enough to take in the air. There's not enough elasticity to let your lungs fully expand. We can actually experience this in small portions if you go through severe anxiety. It will actually simulate this in the body. It's pretty interesting. All right, I think I covered everything. Exam time. Have fun watching this.